Hello, everyone, and welcome to Soil Hydraulic Properties, 8 ways you can unknowingly compromise your data. Today's presentation will be 30 minutes, followed by 10 minutes of Q&A with our presenter, Leo Rivera, whom I'll introduce in just a moment. But before we start, we've got a couple of housekeeping items. First, we want this webinar to be interactive, so we encourage you to submit any and all questions in the questions pane, and we'll be keeping track of these for the Q&A session toward the end. Second, if you want us to go back or repeat something you missed, don't worry. We'll be sending a link to the recording of the webinar via email within the next 3 to 5 business days. All right, with all that out of the way, let's get started. Today, we'll hear from application expert Leo Rivera, who will discuss best practices for measuring soil hydraulic properties that will save you time, increase your accuracy, and prevent problems that could reduce the quality of your data. Leo operates as a research scientist and hydrology product manager here at Meter Group. He earned his undergraduate degree in agricultural systems management at Texas A&M University, where he also got his master's degree in soil science. There, he developed an infiltration system for measuring hydraulic conductivity used by the NRCS in Texas. And currently, Leo is the force behind application development in meters hydrology instrumentation, including HYPROP and WP4C. He also works in R&D to explore new instrumentation for water and nutrient movement in soil. And so without further ado, I'll hand it over to Leo to get us started.
All right. Well, thanks, everybody. I'm really excited to talk with you about these topics today. This is an area that I spent a long time working in, and I love talking and learning about measuring soil hydraulic properties. It's just one of my favorite areas to work in. So just a little bit of introduction about myself. My background is in soil physics and pedology, and throughout my studies and my career here at Meter Group, I've gained about 12 years of experience measuring and interpreting soil hydraulic properties and measuring soil moisture release curves. And throughout that time, I've seen a lot of the right ways you can make these measurements and a lot of the wrong ways you can make these measurements. I've also seen a lot of really interesting ways that you can use these measurements to learn things about soil. And today I'm going to share some of that knowledge with you. So first, I think the best thing, I like to start with this. Why do we even care about measuring soil hydraulic properties? And really, it comes down to this. Soil hydraulic properties impact almost everything soil is used for. It impacts crop production, obviously, with the availability of water, and it impacts our decisions when it comes to making irrigation decisions, how fast to irrigate, how much do we need to irrigate. All of these things are impacted by soil hydraulic properties. It also has an impact on the hydrology of both native and urban environments. And it's also used in landfill performance, trying to estimate the efficacy of landfill covers, whether it's a cover designed to limit the water movement through soil, or if it's a cover designed to store water, those evaporation type covers. It also impacts stormwater system design, both measuring the native soil properties and if you're engineering the soils, what are the soil hydraulic properties of the engineered soils. And one topic that has been much more popular recently is soil health, and how do these properties play in the role of soil health and determining if our soils are healthy. And when I think about these measurements, there are some common issues that come to mind for me when we're trying to make these measurements. Some of the most common issues actually just go back to sample collection, either not collecting a good sample or a representative sample, or not sampling from the right location. So these are factors that can have an effect on the measurement, or not having enough samples. Another issue that we typically see is when we're trying to look at field versus lab measurements and the way they compare. And I'm going to dive deeper a little bit into this later on in the virtual seminar. Another issue that we commonly see is the measurement location and the number of measurements. And so I have this graph here on the right-hand side that shows the typical distribution of hydraulic conductivity in a field. And what you see is that hydraulic conductivity is a log normally distributed property in soils. And so what you can find is if you don't have enough measurements within the field, you're not going to be able to properly quantify the actual hydraulic conductivity of the field. Say, for example, we measured in one of the sites that had the higher hydraulic conductivity. That's going to skew your average high if you don't have enough measurements to actually quantify what the hydraulic conductivity is in the field. And then ultimately measurement quality, whether it's not using the right gear or not using the gear properly. And I'm going to try to cover all of these points in today's virtual seminar. So for today's virtual seminar, here are some of the goals that I'm hoping to come away with at the end of the virtual seminar. I want to go over how many measurements you need and ways to determine that, where to make your measurements, and also how you can use field mapping tools to help determine where to make measurements. We're going to go through some sample collection best practices. We're also going to go through tips for using laboratory instruments. We refer to our laboratory instruments as our Labro suite. Tips for using those instruments to quantify soil hydraulic properties, and then best practices when using field devices like the Saturo to measure soil hydraulic properties in the field. So before we dive any deeper into that, I think it's first to address what actually impacts soil hydraulic properties. Obviously, soil texture is going to have an impact, but it's not the main variable that governs hydraulic properties of soil. Soil structure is going to play a huge role here. How strong is that structure? What type of structure is there? Biopores also have a really big impact as well. You have decaying root channels, we have wormholes and other animals that are interacting in the soil, all creating pores that can have a big impact on the hydraulic properties of soils. Obviously, compaction and bulk density is going to have a big impact on these properties. Water content and water potential. So what I'm referring to here is actually the antecedent conditions of the soil. So how wet is the soil beforehand? Because that can actually play a pretty big role in how the soil hydraulic properties change and what you measure. And then of course, organic matter is going to have a big impact on this measurement as well. So the first piece we want to talk about is how many measurements do I need to make? And you'll notice that this slide is pretty fully loaded with text. And I typically don't like to do that, but I did that here to really convey that there's a lot that goes into determining how many measurements you need to make on a site to quantify the variability. And so that first piece that I want to talk about is how do we account, making sure we're accounting for spatial variability, just like we discussed earlier. And one of my favorite terms that comes to mind when thinking about spatial variability is representative elementary volume, or REV. And what REV tells you, it's the smallest volume of soil that can represent the range of microscopic variations in the soil of that property that you're trying to measure, whether it's hydraulic conductivity, water content, water potential, these various things. That REV value is a value that we refer to as being how big of an area do we need to measure to properly quantify that variability. And one way I like to look at variability is in terms of the coefficient of variation. So typically, the bigger the coefficient of variation, that means we have more variability in the field, and we're going to need to use more measurements to quantify that. So for water flow processes in soil, REV is primarily dominated or based on the soil structure. That's one of the biggest factors that's going to have an impact on how big of a volume you need to measure to properly quantify that variability. Another component that has a big impact is the time domain or seasonal changes. And so what I'm talking about there are things like changes in antecedent soil moisture. What you've seen in literature is that antecedent soil moisture can have an impact on what for example, the hydraulic conductivity is of the soil at that time. This is especially more present in soils that are expansive or shrink and swell. And I'll dive a little deeper into that as we keep going. Changes in vegetation are also going to have an impact over time. Are we going to have decaying root channels, or will we have a big mass of roots in the soil during a time? These can all have an impact on the soil hydraulic properties. And then of course, land use impacts. And I think the biggest piece that comes to mind for me in terms of seasonality is from time of tillage. So if we were to go out and till a field, from the point you till the field to later on in the season, you typically will see a continual decrease in the hydraulic conductivity, for example. As the soil settles, you're going to see those pores become more compacted, and you're going to see a change in the hydraulic properties. And then ultimately, you have to think about your research-specific needs. What are the number of treatments or plots? Are there different locations that you're trying to characterize and compare across? And then ultimately, how much variation do we actually need to characterize for this study? Because it may be that for a specific study, we don't need to do as many measurements because it's just not going to have as big of an impact on the experiment. And ultimately, it comes down to the last piece that it's going to come down to is the actual measurement volume of the device you're using. So typically in the field, you can only have so big of a core, say typically anywhere from a 2-inch to 3-inch core for lab sampling. So you can only characterize so much with that. So that means you're going to have to take more samples to make more measurements. In the field, say we're using a ring infiltrometer, the ring size of the infiltrometer that you're working with, and what are the practical limitations of that? You can only have so big of a ring in the field, and the bigger you go with your ring when you're trying to do these measurements, that typically means you're going to use a lot more water to make these measurements. So now we've talked about how many measurements do I need to make. The next question is, where should I measure? And there are several factors to consider when trying to think about where to measure. Again, we're going to go back and talk about the number of treatments. So if you're dealing with plots, obviously you're going to want to try and characterize those different treatments within your plots. You're also going to want to look at if you're measuring in different locations, because you can see variability due to soil type and those types of things. Obviously changes in soil type, are there changes in soil type within the field or changes in soil type across the different locations that you're measuring? One of the bigger factors that can have an impact is the topography and landscape position and the processes that occur across these different topographies and how the soil forms. Land use changes. So here you see an example of 3 different fields in a improved pasture on the top right corner. The left image is of a conventional tillage field, and the bottom right image is of a native prairie. And so if you're trying to look at and characterize different land uses, so here's a good example of how you're going to try and factor where to make your measurements. Then also looking at field traffic, do you have rows where your tractors are constantly driving across? You're going to have more compaction there, or in the field, say for example, out in forested sites, your tracks where people are typically driving across, moving equipment and lumber and those types of things, where are you going to see bigger zones of compaction? And that may govern where you need to make measurements to characterize the variability. So when we're trying to think about how we decide where to make our measurements, there are tools available to help us think about this and make decisions on where to make measurements. And one of the first things that comes to mind for me are elevation maps. And the reason I like to use elevation maps is I first want to talk about the Katina concept. And the Katina concept kind of describes how soil formation processes change across a hill slope. Say you start from the summit, moving down the back slope of the hill slope to the foot slope. Those differences in this landscape position cause a really big difference in how the soil forms in that area. And that can result in variability in different soil hydraulic properties. So it's important to look at these different examples and try and quantify across that potential area of variability. And the nice thing about elevation maps is there's a lot of tools already available to help us characterize this. There are GIS tools available with existing data that we can use to characterize the landscape. It's also not very hard to go out and make these surveys. And really, ultimately, elevation and changes in landscape position are pretty easy to visually identify in the field without needing maps. So that's a good place to start. But if we want to go deeper and try and do a better job of characterizing variability within our field, another option are electrical conductivity maps. So there are tools that measure the soil electrical the apparent soil electrical conductivity that can help us identify variability within a field. One of those tools that you can see here in this middle image, like the EM38 device from Geonics, can be used to do surveys using a sled like you see in the bottom image and passing it across a field to make these measurements. So here you have an example of this same field that we were referring to with the elevation map. Now we've overlaid our EC map as well to help characterize these zones of variability. Now, when looking at apparent electrical conductivity, there are several factors that can impact this measurement. Some of the main factors are salinity, changes in depth of parent material, soil texture, clay type can also have an impact, and then of course the soil moisture at the time of the measurement also can have an impact on this property. So typically it does require a little further investigation to understand where this variability is coming from. For example, in this field that we show here, the primary driver of this change in the bulk EC was the depth apparent material. And that actually helped us identify the different soil series between Houston Black and Hayden Clay, for example, in this field. So the last two field mapping tools we talked about typically require some going out in the field and making measurements, or you pulling data from an existing place. Another tool that's freely available that I really like to use when it's not possible to go out and do these surveys is Web Soil Survey. Web Soil Survey is a free tool from the USDA NRCS that allows us to actually go in and look at the potential changes in soil type based on what was mapped by the NRCS within a field. So here we see that same large area. So you can see that one field that we were working in the middle, and what were the soils that were mapped here. Now, the issue with Web Soil Survey, of course, is it's a larger scale of observation. They don't go out and fully characterize everything down to the meter, but it's something that at least gives us an idea of where we might see variability within our field. So it's a useful tool when it comes to that practice and just trying to look at variability, especially if you can't go out and use some of these other tools to characterize that variability. So now that we've talked about how many measurements and where to make our measurements, it's time to go out and take samples. And so here are some best practices that I like to think about when going out and collecting samples, whether it's actually going out and doing the measurements or collecting samples to bring back to the lab. One of the first pieces that we need to think about is intact versus repacked cores. The reason I bring that up is a lot of these properties that we're looking at are primarily affected by soil structure and the way the structure of the soil is in the field. So I typically recommend trying to get an intact core if possible. But if you can't, then a repacked core, you want to try and shoot to repack the core to the same density that it was in the field. But ideally, we can use intact cores because it's still not going to represent the structure of the soil in the field. When you're out in the field collecting samples, I often recommend recording site information. So try and get location and GPS coordinates on where you've collected your samples. What's the bulk density? Especially if you're having to repack the cores, you're going to want to know what the bulk density was in the field. Measuring the antecedent soil moisture just to help as you're trying to characterize changes, knowing what the antecedent soil moisture was at the time. And then of course what the vegetation is in the field, because vegetation can have a big impact on why these properties are changing. When you're trying to collect samples, you often have to deal with things like rocks and roots. And depending on the size of the rocks, you may want to try and collect, if they're small gravel, then you're going to want to try and collect it as it is with the gravel pieces in the soil, because that's how they are in the field, and they're going to affect how the soil behaves. But sometimes it's just not possible, so we have to work around large rocks. It's just something you're going to have to work around and figure out what's best for your research and for the project at hand. I often recommend collecting duplicate samples. You never know what's going to happen with the sample that you collect. Something could go wrong when you're trying to prepare it. It's always good to collect as many, at least duplicate samples, and you may want to measure on both samples anyways to help characterize the variability depending on how big your samples are. And one last piece is dealing with expansive soils. Expansive soils make everything that we do in the field tricky. When you're sampling, I often recommend trying to sample in expansive soils when the soil is near field capacity, because at least when you do this, you're sampling when the soil's at its more fully expanded state, and it's less likely to swell up, say for example in your ring, when you start adding water, which will obviously affect the properties of the soil after that. So now that we've got our sample, let's talk about measurement best practices and how to actually use the samples in the lab, or how to make the measurements in the field. And before we go too deep into that, I want to just address some of the differences between lab measurements and field measurements. So I've got a slide here that has a table that shows several different strengths and limitations of both lab measurements and field measurements. But I'm going to address some of the primary ones that I've got bolded here. So when we're looking at lab measurements and lab instrumentation, some of the strengths of these measurements are you can control the conditions, and you don't typically have to correct for three-dimensional flow. It's a lot easier to control these things. And most lab instrumentation, you can have automated and relatively fast analysis and easy to use tools for that. The limitations of lab instrumentation is it doesn't take into account the field conditions and the soil around it. There's a lot of things that can vary between the two, and it's really hard to compare lab versus field measurements. And with field instrumentation, some of its strengths are it really helps us understand the variability in real-time field conditions. This is the best measure of how are things actually going to happen in the field. And there are tools now that are automated that help make this measurement easier, because it is something that takes time typically. So if we can have automated tools, it really helps to make this measurement easier and helps reduce some of the potential error in the measurement. Some of the limitations, again, it's uncontrolled conditions. We can't control everything that's happening in the field. We can't control what the soil moisture is at the time, and we can't control where the pores are going. And sometimes weird things happen when we make these measurements in the field. And ultimately with field instrumentation, this also applies to lab instrumentation as well, but poor installation can really have a big impact on your accuracy and affect the measurement. So first, for best practices, we're going to talk about lab measurement best practices. And again, we refer to our laboratory devices as our Labro suite. So you're going to see that term used quite a bit throughout these next few slides. So when we're thinking about making measurements in the lab, I think it's ultimately important to understand what the limitations are of these lab devices. And it's going to vary depending on what type of instrument you're using. But again, like we've talked about with laboratory instrumentation, your sample volume is typically small. It's really hard to get a big sample and actually run it in the lab. So in order to properly characterize the variability, you may need to make more measurements to characterize that variability. And it really depends on what you're measuring. With hydraulic conductivity, you're typically going to need a larger REV to characterize that variability. With water content and water potential, because it's more of a linearly scaled property in the field, you don't need as big of a sample or as many measurements to characterize this. Another issue or another limitation is for water potential specifically, there is no device that covers the full range of water potentials. So here on the right, we have a chart of different instruments and different techniques and what ranges of water potential they measure. And you see there's no device that really covers the full range, especially with good accuracy. And so it's important that you understand this limitation. And if you're trying to characterize the full range, you're typically going to have to use at least 2 devices to make this measurement. So for example, the HyProp and the WP4C together. And it's also important to understand the limitations of the devices when you're trying to measure KSAT in the lab or unsaturated hydraulic conductivity. For example, with the evaporation method, there are some limitations when trying to measure the unsaturated hydraulic conductivity near saturation. And then with KSAT, just understanding you may have open-ended pores and how you need to treat the sample. There's just some things that you need to understand. You'll have to just take into account there in terms of its limitations. So the next thing to think about for best practices is which properties are actually critical for my measurement. And the first thing I think about is which range of water potential is most critical for what I'm trying to study. Am I primarily interested in water flow properties? So that means I maybe only need to measure between 0 and -10 kPa. Or am I interested in plant available water? So I need to measure from probably about field capacity down to permanent wilting point. And ultimately what ranges is of most importance. Another piece to look at is actually what range is the water being held at in the soil that I'm measuring. So for example, here on this graph here on the right, we have 2 different soil moisture release curves. We have a soil moisture release curve for a silt loam and a soil moisture release curve for a loamy fine sand. And both of these samples were measured using the HyProp and WP4C together. But what's interesting is you look at the loamy fine sand, you see that the majority of the water is held in the very wet range, and it would have been primarily measured with the HyProp device. So really what you need to think about is, am I looking at coarser textured soils or fine textured soils? Say for example, if we were to only use the HyProp on the silt loam, we wouldn't have characterized a big chunk of where the water is being held in that soil. So it can be important to use both devices for finer textured soils. And for coarser textured soils like sands or soilless media, you can often get away with just using one device like the HyProp to characterize the soil moisture release curve. And then again, it's important to understand, are you primarily interested in unsaturated hydraulic conductivity or saturated hydraulic conductivity? If saturated hydraulic conductivity isn't really important for your study, you obviously don't need to make that measurement. But if it is, say for example, you can't just use the high prop and its measurements of unsaturated hydraulic conductivity to characterize the saturated hydraulic conductivity due to its limitations near saturation. So you'll need to use another device like the KSAT to measure the saturated hydraulic conductivity of that core sample. And again, I'm going to hit on understanding limitations. So when we think about field measurements, we get complete soil interaction. With lab measurements, it's a single point assessment of wherever we take that sample. So it's not going to fully characterize how the water is flowing through the soil throughout the entire soil profile. And so we're going to need to make measurements at all of these points to try and bring all of that together and understand what's happening. So now that we've talked about all of the pre-parts of the measurement and understanding what instruments you need, now let's think about, okay, I have my measurements, my instruments ready. I'm going to be making measurements. What are the things I need to think about when I'm making these measurements to get the best results? And one of the first things that comes to mind for me is actually accounting for hysteresis. So what I'm referring to here is a wetting versus a drying curve. And on the graph here on the right, we have an example of a measurement from the high prop that's on a drying curve and a measurement from the WP4C that's on a wetting curve. And due to hysteresis, we actually get a gap between the two. And so it's important to understand that with the high prop, the evaporation method, you're measuring on a drying curve, and that's the only way you can make that measurement. With vapor pressure methods like the WP4C, you can measure on a wetting and a drying curve. So it's really up to you on how you want to prepare those samples and how you want to bring those data together. But if you want to get the best matching between the two devices to characterize that full soil moisture release curve, then you're going to need to try and match that up and try and collect both measurements on a drying curve. And one of the best ways to do that with the high prop and the WP4C together is actually to subsample from the high prop sample and bring that over for making your measurements in the WP4C. And the way we do this is we actually subsample from both ends of the core. And the reason this works is, one, that core sample is already on the drying curve. And if you think about the way the evaporation method works, you're going to have evaporation from the surface, and that's going to create a gradient throughout that core sample. So what we do is we subsample from the top and bottom end of the core sample, which is going to give us our driest point and our wettest point. And then we start pressing the sample out of the core and dissecting it into different sections, usually 2 or 3 different sections, and trying to collect that intermediate samples at those 2 or 3 different points. And what that does is it gives us several samples along the drying curve. And then we can easily just take those samples and run those measurements in the WP4C and get really nice matching of our retention curves from the 2 devices. So another thing that we have to think about when we're trying to characterize the full soil moisture release curve is actually looking at matrix versus osmotic potential. So with the evaporation method, we're using tensiometers to make the measurement. Tensiometers only measure matrix potential. Vapor pressure methods measure both matrix and osmotic potential. So what you can see in this graph here is, if you have a sample that has an appreciable amount of salts, you can get a deviation as you approach saturation due to the impact of osmotic potential and how it becomes more dominant as we approach saturation. So what can you do? It is possible to separate the osmotic component from the vapor pressure methods. And we do this by measuring the saturated extract EC of the sample and then calculating what the osmotic potential is at the different water constants. And that allows us to then remove the osmotic potential from the vapor pressure methods measurement and then apply that and input those data into our fitting software and allow that to be just a comparison of the matrix potential components of water potential throughout the curve. So we've talked about some best practices for the lab measurements. Now let's talk about best practices for field measurements of hydraulic conductivity that we would involve using some type of ring infiltrometer. In these examples, we're going to primarily refer to the Saturo device, but all of these best practices apply to any type of device you're going to use in the field. So before we go out in the field, I always like to start with a pre-field checklist. So the first thing we want to do, obviously, is make sure we have the tools available that we're going to need to make the measurement. Just make sure it's the right hammers. We have all the tools that we're going to need to use, whatever device it is that we're making measurements with, water containers, those types of things. It's always good to just make a checklist and make sure you have all those tools before you go out in the field. Another important kind of pre-field checklist or thing to think through is selecting a water source. And water chemistry can have a really big impact on the measurements of hydraulic conductivity in the field. So you have to take that into consideration. Do you need to use artificial rainwater to more simulate the infiltration of rainwater? Or are we trying to simulate irrigation water moving through the soil? So it's what are we trying to look at? And as you think about that, if you're going out in the field trying to measure the movement of irrigation water through the soil, it's best to choose water from that source. That way you're matching up the chemistry. Or if you're trying to simulate rainwater movement, then bring out your own source of artificial rainwater. It's also really helpful to have a characterization sheet when you go out into the field. So here's an example in the middle of a characterization sheet that we use for a lot of our field campaigns, whether we're trying to install sensors or going out and making these measurements. And it helps us pull information on landform, vegetation type, and land use, other pieces that we might want to look at, characterizing what the soil properties are. These are just really useful things to have, and we'll include a link to this characterization sheet in the follow-up to this virtual seminar. Now that we've got all our tools and we're ready to go, the next is site selection. And the first thing that we think about in site selection, obviously, is making sure that we're measuring in the right location that represents our fields, but also having to work around things like large rocks and roots. So if we have large rocks or roots present, we're typically going to have to try and work around them because those just make the measurements really difficult. If it's a gravelly soil and they're small gravels, then those are fine. We can work with those and insert rings into those soils. We just have to be careful. That typically means our rings are going to get a little more nicked up, and we're probably going to have to file them down more regularly. Another important thing to think about when going out in the field and site selection is dealing with expansive soils. So here we have an example of a large crack that can form in these vertisols that we often have to work with, especially where I did my graduate studies in Texas. I primarily worked in the Blackland Prairie of Texas, so all of my measurements were on vertisols. With vertisols, they can form these large cracks. And I went out to go make a measurement once, and I wasn't really paying attention. I didn't realize there was a large crack on the site that I was trying to measure. And I actually wound up going through 500 gallons of water in about 2 hours, which is insane to think about. So when we're thinking about making these measurements, it's actually really important to try and time these measurements during the right time of year, especially with these cracking soils. So ideally, what I would like to do is go out when these cracks aren't present or try to avoid the cracks. Typically with vertisols like this, it's best to go out during the wetter season when the soils are more near field capacity and there's less likely to be large cracks like this. There are other ways to characterize the impacts that cracking soils can have on the hydrology of soils outside of making these measurements. So it's best to try and avoid them in the field if possible. It's not always possible, but trying to work around them as much as possible as you can. So now we've got our site selected. It's time to start actually preparing the site for the measurement. One of the first things we're going to want to do is trim any tall vegetation to keep it out of the device from causing too many issues with the sensors and just trying to make the measurement. So I typically recommend going out with some hedge trimmers or clippers or whatever to try and trim down any of the tall vegetation, at least down to about 3 or 4 inches. It doesn't need to be super short. And ideally, you don't want to make it too short anyways, because the shorter you make it, the more likely you are to disturb this whole surface. And we want to try to avoid that because we want to try and make these measurements representing what the field conditions are. If there's any large debris, let's try and remove that out of the way. That way, especially if there's any large branches, that's going to cause difficulties when trying to insert our rings into the soil. And now that we have our site ready, the next question is, well, I have different options of ring depths. I have a 5 centimeter or a 10 centimeter insertion ring. Which one should I use? Ultimately, this comes down to 2 things for me. It comes down to the soil structure. So I typically recommend using the 5 centimeter ring for soils that have strong structure and are going to hold up well, because the 5 centimeter ring is going to have the least amount of impact on the insertion depth, or sorry, the least amount of impact on the soil and disturbing the soil. So it's going to have the least disturbance. But for structureless soils like sandy soils, or soils that were recently plowed, we're probably going to want to use a 10 centimeter insertion ring, because that's going to help the soil hold up better to us trying to infiltrate water into it. And it's going to be less chance of, or less likelihood of, any bypass flow being created as the water moves through the soil, potentially disturbing the soil. Another thing to consider is the duff layer. In forested sites, there's often a very thick duff layer, and we're going to need to use a deeper ring to help get through the duff layer into the actual soil. So in that case, as I recommend using, in that type of situation, I recommend using the 10 centimeter insertion ring. And now we've got everything decided. The next part is actually just inserting the ring into the soil. And one of the most critical things here when inserting the ring is trying to prevent air gaps. So you always want to inspect the inner part of your ring and make sure there's no damage or nicks that could potentially create a channel as you insert the ring. And ultimately, you want to have care when you're inserting the ring. You're going to need some force to drive it down, but carefully make sure that the ring is going down straight and not moving side to side, because this will also prevent air gaps. Anytime you create air gaps around the ring, you're going to have bypass flow, and it's going to artificially push your measurements high. So always check this after you've inserted the ring. I often recommend using like the pencil end of a eraser or your finger to go and tap the soil around the edge of the ring, just to make sure you have good contact there. So now that we have everything set up and we're ready to make our measurement, one thing you need to keep in mind is, in the field with these devices, no matter what type of infiltrometer it is, there's going to be three-dimensional flow, and we need to make corrections for that three-dimensional flow. So are we going to have to make estimations of the soil properties? So you might want to collect information on what your soil properties are. That way you can go back and reference that post when you're trying to make the corrections for three-dimensional flow, because these are primarily dominated by what the sorptivity of the soil is, and that's dependent on soil type, structure, and various components. Now, that's a lot of guessing. And one of the things that we've done with the Saturo is we've tried to take out the guessing by using the dual head method. And you can see the equation here that we use, where we infiltrate water at two different pressure heads to actually directly estimate what these properties are. So with the dual head method, now that we're going to use this method to make our estimates make our corrections for three-dimensional flow, there are a few things that we need to think about when adjusting these settings of what pressure heads are we going to infiltrate water at. Obviously, it's going to be the soil type. Primarily, the main thing you want to think about is you want to drive enough difference between the two pressure heads to be able to measure that difference. That way we can use that in the corrections for three-dimensional flow. So soil type is going to have a big impact on that. Typically, soils with higher hydraulic conductivity, you can go with a lower pressure head difference. Soils that have a lower permeability, you're probably going to need to increase that pressure head difference. Also, antecedent soil moisture. So how long do I actually need to measure to approach steady state? If I'm closer to field capacity, I can probably get away with only measuring for maybe 90 minutes. In some cases, I may need to measure longer. And then the last piece is looking at macropores. The more macropores that are present, the longer you're going to have to make your the higher the hydraulic conductivity is, and the less pressure head difference you'll probably need to actually make that measurement. So to summarize everything up that we've discussed, hopefully I've given you enough information to help understand how many measurements you need to take to quantify variability and look at that REV. You'll have some information on knowing where to measure and how you can utilize field mapping tools to make that decision. Gone over some tips for collecting quality samples. And ultimately, it comes down to following the appropriate best practices for your instrumentation in the field. Now we'll go to questions.
Great. Thanks, Leo. We'd like to use the next several minutes. We'll see if we can get to 10 minutes here to take some questions from the audience. Thanks to everybody who submitted questions. We've got a bunch of great questions already that have come in. And there's still time to submit your questions. We'll try to take as many as we can. But if we do not get your question, we do have them recorded, and Leo or somebody else from our meter environment team will be able to get back to you via email regarding your question specifically. So please submit any and all questions, and we'll try to get to as many as we can before we finish here. Okay, so Leo, expansive soils, those seem to be an issue. I swear I've got a crack in my backyard. I just I waste so much water. Anyway, but enough about me. Is there a quick and easy way to identify whether you have an expansive soil type?
Oh, that's a really good question. it's really obvious to go out and look in the field at different seasons and see if you have cracking forming. But ultimately, I would recommend just looking at your soil survey and identifying what soil type that you're trying to measure, and looking at the properties that are described by the NRCS. One of the things they're going to give you is a coefficient of linear extensibility typically, and the higher that value, the more expansive your soil is. So most soils have a 0 to 0.01 coal value, but in these clay soils, we can have up to a 0.18 coefficient of linear extensibility, which means you're going to have a more expansive soil, obviously. So that's one way to look at that and identify that.
All right. And then how can you measure that impact of cracking soils on what impact it will have on infiltration?
Yeah, so cracking soils make it really difficult to measure these properties in soils. And so some of the work that we've done while I was at A&M was actually using tools to measure the crack volumes throughout the season, and then actually characterizing how fast the water would flow based just on the geometry of the cracks in modeling, because it's nearly impossible to make these measurements when the cracks are big like that. I mean, that measurement where we had 500 gallons go through the slope, even though we used all that water, we didn't get a good measurement. So I often recommend trying to actually characterize the cracking volume in your soils, and then just using modeling to characterize the impact it has on the hydrology.
All right. How do you deal with rocky soils when it comes to interpreting data, calculating conductivity, those kinds of things?
Yeah, rocky soils are a lot like expansive soils, make things a lot more difficult. If the rocks are small enough, I try to make the measurements with the rocks present like they are. It's not always the case. We have sometimes really large pieces of rock that you just can't make these measurements because you can't even insert the devices. So what I typically recommend doing is removing the rocks from the sample. This is typically going to be a lab-based measurement, characterizing the soil itself, and then trying to correct for the volume that the rocks would have on that would have in the soil. That way you can at least know how the soil is going to behave, and then we can try and adjust our modeling based on the rock space or the volume of rocks in the soil.
You also touched on soil cores repacked versus intact. Can you explain a little bit what differences you might see in the measurements in the lab, and how significant might those differences be?
Yeah, definitely. So with lab samples, repacked versus intact cores, the biggest piece is the structure of the soil. And when you repack soils, you're not able to represent that structure. It's impossible. And the structure can have a lot of macropores around it that can have a much higher hydraulic conductivity than what you would see in a repack sample. So once you remove that structure, you're not really characterizing the impact the structure that it's going to have on the measurement, especially for hydraulic conductivity. It's not as bad for some of the other properties, but it has a big impact on water flow. And so you just lose that. And there's really no way to model that. So that's the best thing to do is just try to leave it intact and make the measurement as it is.
All right. We do have a lot of great best practices questions here, so it's good to see. How do you deal with slopes?
Oh,
I'll just
yeah.
like that straight
No,
up.
that's a good question. So with slopes, you actually can make the measurement on the slope as it is. So typically what you want to do, like say you're using a ring infiltrometer in the field, whether it's the Saturo or another type of ring infiltrometer, what you want to do is at least make it to where the ring is driven in the same depth. So the ring's going to be along the slope, and you want to just maintain your average water height at the center of the slope. So say we're setting it to 5 centimeters, we're going to set our sensor that measures the water height at the center of the slope. That way we're maintaining an average depth of water throughout that measurement. And ultimately the measurements usually come out perfectly fine on slopes versus flat sites.
All right. Let's see, I think we'll have time for a couple more here before we sign off. Can you elaborate a bit more on REV and the number of samples needed to represent physical and chemical properties there?
Yeah, so this is actually one of my favorite things to talk about, and I actually hope to do a chalk talk on this later on down the road where I dive a little deeper into it. But REV, or representative elementary volume, it ultimately depends on whether you're looking at a linear process or property that it's more linearly distributed throughout the field, like water content, or a log normally distributed property like hydraulic conductivity. So when you're dealing with physical or hydraulic properties like hydraulic conductivity, because they're log normally distributed, you typically need a bigger measurement volume to characterize that variability. Some of the more linear processes and chemical processes may fit into that category. I'm not a soil chemist, but if the chemical processes are more linearly distributed, then you can get away with a smaller measurement volume. There's a really great chapter on this in the methods of soil analysis. I highly recommend just reading that chapter and diving deeper into it, but hopefully I'll do a deeper dive later on down the road into this topic.
All right. I think we'll get to, well, let's do 2 more. All right. Here's one, and this kind of gets to a bigger meta discussion about how to explain our results from any scientific endeavor to the layperson as well. But when relaying KSAT to a farmer, sometimes things don't translate, right?
Yeah.
But infiltration rate always does, or seems to, at
Yep.
least from this individual. Is there a way to calculate infiltration rate from the KSAT data given by the SAT row?
Yeah, absolutely. So ultimately, infiltration rate is the raw data that's actually measured. So with any of these measurements, we're actually measuring infiltration rate and then calculating hydraulic conductivity. So what you can do is go in and actually just look at your raw data and just take an average of a certain time snap. Typically, I recommend using the lower pressure head data because the higher the pressure head is going to push your infiltration rate higher. But you can use that just to calculate what your infiltration rate is, just based on the average of those measurements. So that's ultimately, all these measurements are measuring the infiltration rate.
Okay. Last question, and I'm gonna cheat and squish a couple of questions together. But what property has the biggest impact on EC mapping? And then to piggyback on that, what can the zones created by EC mapping vary by season?
So there are a lot of properties that can have a big impact, and ultimately depends on your field. For example, we had several fields that we measured that had a big difference in soil type. So we had a field that ranged from a sandy soil all the way to a clay. So that's gonna be your dominant variable there. But in soils that are more, what you would say maybe a little more homogeneous. So say that one field that we showed that was all clay throughout, the biggest factor that had an impact there was the depth of parent material. But it really varies field to field, and that's why you have to go through and characterize at least a little bit about the field to understand what the zones are representing. And then to talk about how it can vary season to season, it can, because water content also has a big impact on this measurement. And if you're going to see differences in your zones of water content, we'll call it, or how the water is distributed across the field seasonally, you can see differences in your EC maps based on that. And so remember, it's just giving you an indicator of what variability is, or what the variability is.
Right. Thanks a bunch, Leo. That's going to wrap it up for us today. Thanks again for joining us. We hope you enjoyed this discussion as much as we did. Thank you again for all the great questions. We had dozens of questions we didn't get to. But again, we have them recorded, and Leo or somebody else, another expert from our meter environment team, will be able to get back to you via the email that you registered with to answer your questions specifically. Also, please consider answering the short survey that will appear after the webinar is finished to tell us a bit about what types of webinars you'd like to see in the future, and other items as well. And for more information on what you've seen today, again, visit us at metergroup.com. Finally, look for the recording of today's presentation in your email, and stay tuned for future meter webinars. Thanks again, stay safe, and have a great day.